Hello, my name is Nuri Iziani binti Ramli. So today I will present on MC2 project on placement and routing automation. So in this project is we are given an objective to explore physical placement and global routing optimization for cell digital design using a Verilog netlist as input. So for my approach, I use custom Python script to automate the netlist parsing, including also placement optimization and routing visualization. So in my approach, I'm optimizing the placement using simulated annealing to ensure that the cost, which is half parameter wire length HPWL, is minimum as it can be, and also reduce the routing congestion using a Manhattan style method. So in the left side here is the standard cell design module, which contain of several gates or installation of module of this netlist. Yeah. So so in my code, this netlist.v will be load into the Python script, and it will also process the netlist file to find the to find all the nets or the gates inside, and also get the data of input wires connecting between how the input wires are connecting, input and output wires are basically connecting to each of the gates, and it will do initial placement and compute the initial HPWL and visualize the initial graph. So on this part is so this is the code placement.py. So here is where we define we define the netlist or the Verilog file that we want to extract, all the gates and the nodes. And we also I also define here what kind of gates or module name that I would like to extract, and it will process all the module, wire list, how many gates, and the structure of the gates, and print out a summary for me. And also after that, it will randomly position the gates according to the wire connections, and compute the HPWL, and then visualize the placement. So this is the initial placement of the whole netlist diagram. So you can actually compare it to the netlist.v, where U1 output is actually connected to U2, and so on. So I had verified that every connection is correct, and then I will pass this to the optimization process, which is using simulated annealing, and also to compute to compute the lowest cost, which is the HPWL. So after we've done this, we pass into these functions, the gates and the position, and it will start to process and get the current cost. Also iterates for each of the process to like randomize the position, and calculate whether it's the best position based on the HPWL value. And then if it is, then it will accept that as the current as the best cost, and save it as the current positions. And this one is just standard step in simulated annealing, where we will keep repeating until we get until the temperature is less than or equal to the value that we set here. So and then so in this case, I iterate this for 5,000 steps to ensure that each of the optimized positions are covered. Yeah, and then we will visualize the graph and calculate the difference between the final optimized position versus the initial one. Yeah, so this is the log of the entire Python script. So you can see here how is the initial position and the initial HPWL, and the final one at least reduced by 10 units, and percentage of improvement is 45%. So this is how the optimized placement looks like. So it's, if you compare between the two, you can see that it use lesser and lesser area as well, and it also has less wire congestion, which which may prevent any heating that can be caused from the wiring overlapping. Yeah, so this is the result of my approach. Yeah, so I think that's all for my presentation. Thank you.